Hi, welcome to Orozco's Lectures. I am Jose Orozco, and these are my lectures. This lecture is a pre-calculus lecture. I hope you enjoy it.
This is chapter 1.9, which is on inverse functions. There we go. All right, so first let's start with a definition. Let f and g be two functions such that when you compose them with each other, so in other words, f composed with g of x, you end up with x for every x in the domain of g, and when you compose g with f, so g composed with f of x, you also get x for every x in the domain of f. Recall in the first one here, g is the inside function, and the second one here, f is the inside function. All right. So now, under these conditions, the function g is said to be the inverse function of f. All right. And in here, we're going to denote that as f inverse. All right. This is pronounced f inverse. So essentially, we have f with an exponent of -1. All right. That means f inverse. Don't confuse it with the reciprocal. Now, so what we're saying here, using this notation now, we can say that f composed with f inverse of x gives us x, right? Because I'm just replacing g now. And f inverse composed with f of x is also equal to x, because now over here, I'm replacing g with f inverse. All right. So one thing that we also must keep in mind here is that the domain of f must be equal to the range of f inverse, and similarly the domain of f inverse must be equal to the range of f. All right, so what does this mean? The domain of f must be equal to the range of f inverse, and the domain of f inverse must be equal to the range of f. So let's say, for example, that here is the domain of f. All right, and we have some x here. Now we're going to go here from x to f of x using the function f. And now over here, this is our range of f. But since the domain of f must be equal to the range of f inverse, what we can say is that, and also the domain of f inverse must be equal to the range of f, we can say that over here, this is the domain of f inverse, and we go back this way using the function f inverse into our actual output of x. Over here, this would be the range of f inverse. All right. Now, I want to make a very important note here that I mentioned earlier. F inverse is not the reciprocal of f. All right. Here on the left, we've got f, the inverse of f. Let's write it that way. The inverse of f. On the right here, we've got the reciprocal of f. We're used to having that exponent of -1, meaning reciprocal. That's true for variables, it's true for numbers in general, but it is not true for functions. All right, it is not true for functions. If I wanted to talk about the reciprocal of a function, I would have to write it this way, f of x, and then that to the -1. This is the reciprocal, all right? But if I have that power to the -1 there in here, I'm saying f inverse. All right, so that's just some notation. Now, let's see whether two functions are inverses of each other. So determine if the given functions are inverses of each other. So what does that mean? Well, by definition, we have to make sure that this piece right here is true. That when I compose f with g and when I compose g with f, I end up with my output of being just x. All right, so that's what we're going to need to do. So let's look at an example. So let's say here that I gave you f of x being equal to 5 over x minus 2 and g of x being equal to x minus 2 over 5. Right, so what we're going to do here is compose them with each other. So let's say f composed with g. What would that be? Well, in here, this would be f of g of x, right? That's what composing means. And, but what would that mean? That means plugging g of x into the x over here for f. So we have 5 over g of x minus 2. And then what do we know about g of x? G of x is x minus 2 over 5. So this gives us 5 over x minus 2 over 5, and then that minus 2. And what we could try to do here is, let's get rid of this fraction down here. So we want to simplify this as much as possible. And I'm going to do it by multiplying by 1. All right, that fraction there is just 1, 5 over 5. And what would that give us? Well, let's see. 5 times 5 is 25. 5 times this function, times this fraction, the denominator cancels out. So we have x minus 2 minus 5 times this 2 is 10. So we end up with 25 over x minus 12. Notice that this is not equal to just x, right? Since this is not equal to just x, we can just go ahead and say here that these are not inverses. All right, because we needed this to simplify to just x, right, by the definition. So in here, these are not inverses. You'll notice though that these are reciprocals of each other. All right, so in here, I just wanted to show you that reciprocals does not mean inverse. Let's do another example. B. Let's say that I have f of x being something like x minus 4 over 7 and g of x being 7x plus 4. And again, we need to check what we get when we compose them with each other. So first I'm going to start with f composed with g of x. And in here, what do we get? We get f of g of x, which means plugging g of x into f. So I have g of x minus 4 over 7. And then what was g of x? 7x plus 4. So I have 7x plus 4 minus 4 over 7. You'll notice that these parentheses aren't really doing anything. So we have 4 minus 4 goes away. So we end up with 7x over 7, which reduces to simply just x. Good. Now we need to also check the other way around. We need to check that g composed with f also gives us that. All right. So let's see. In here, we're going to start with plugging in f into g. So we have g of f of x. And this by definition means plugging f into g. So I have 7 times f of x plus 4. And then what was f of x? F of x was x minus 4 over 7. So I have 7 times x minus 4 over 7. You'll note there that the 7's cancel each other out. Oh, hold on. I still have this plus 4. Plus 4. All right. Now you'll notice that these 7's cancel each other out. So we end up with x minus 4 plus 4. These parentheses aren't really doing anything. So negative 4 plus 4 is 0. So we end up with just x, which is good. So we ended up with just x in both of these. So what this essentially tells us now is that g of x is the inverse of f. All right, that's what this tells us. So yes, these are inverses of each other. All right, so to verify that two functions are inverses of each other, you plug them into each other, you compose them with each other, and make sure that in both ways it simplifies down to just x. All right, in both scenarios. All right, now graphically speaking, we can say something about a function and its inverse. All right, so inverse functions are symmetrical about the line y equals x. All right, so for example, if I had my x and y axis, right, and I had, well, first let me graph the line y equals x. So in here, this dotted line would be y equals x. All right, so this is y equals x. So let's say that I had some function like this. All right, let's do this. All right, there we go. That's our function. So this is our function f. All right, in blue here we've got the function f. Well, what would its inverse look like? Well, let's see. I'll do it here in red. Its inverse would be symmetrical about this line. So in other words, it's a mirror image about this line. So something like this. All right, here in red, this is f inverse. Notice that this point here where they intersect this line y equals x and this point over here, it's happening on both of those lines, right? It's happening on both those curves, on f and on f inverse, which it should. All right. What else should we notice here? Well, let's take a look at this. This point right here, let's say that that's 0 comma b. All right, some value b. Well, this point over here would be b comma 0. All right, because the domain and the range switch. So the x values, so this x value becomes the y value, and this y value becomes the x value. All right, and that would be true for this one over here as well, for these two. All right, in here, these two, let's say that this one is at 0 comma a, then this one is going to be at a comma 0. All right, domain and the range switch. In general, if I've got just some generic point here, let's call that c comma d. Well, this point over here, the one that's symmetrical around this, would be the point d comma c. All right, because again, the domain and the range switch. In other words, all the x values and the y values switch. Now that's just something to keep in mind about functions in general. Now, when would a function have an inverse? All right, not every function has an inverse. Let's talk about which functions do. And before we do that, we need to first discuss a type of function. All right, so let's talk about something called a one-to-one function. So one-to-one functions. All right, and for the one-to-one functions, well, first let's start with something called the horizontal line test. Horizontal line test. All right, we can abbreviate that HLT, horizontal line test. A function f has an inverse if and only if no horizontal line intersects the graph of f at more than one point. All right, So essentially, this horizontal line test, it's very similar to the vertical line test, but now we're talking about horizontal lines. All right, it cannot cross it. It cannot cross a function at more than one point. So that would be for the horizontal line test. Now, what is a one-to-one function? So let's define that. All right, a function f is said to be one-to-one when each value of the dependent variable corresponds to exactly one variable or one value of the independent variable. All right. Now, what is that really saying? This is just a fancy way of saying a function f has an inverse if and only if it is a one-to-one. All right. So this is saying a function f has an inverse if and only if it is one-to-one. Now, up here, we said that a function has an inverse if and only if no horizontal line intersects the graph of f at more than one point. So, combining these two statements, what we're really saying is that a function is one-to-one if and only if it passes the horizontal line test. Also, if it passes the horizontal line test, it is one-to-one, right? And if it happens to pass a horizontal line test, then it would have an inverse. So, for example, if I had a function like this, right? This passes the horizontal line test, right? Because no matter what horizontal line I draw here, it would not hit the function at more than one point, all right? So this passes the horizontal line test. Therefore, this would actually have an inverse, all right? This function would have an inverse. Let's look at a different kind of function. Let's say that I had this function, right? So this is a quadratic function. This fails the horizontal line test, right? So this fails horizontal line test, which tells us it has no inverse, right? Because it fails the horizontal line test. So like here, like we were saying, this passes the horizontal line test, so it tells us that an inverse exists. So this function has an inverse. Has inverse. And this is has. Let's write that better. Way better. Good job. All right. So this passes the horizontal line test. This doesn't. Now, let's look at another one. What if I had something like this? All right. Now in here, you may be inclined to think, oh, look at that. It passes the horizontal line test. However, this is not a one-to-one function. How come? Why is this not a one-to-one function? Well, simply put, it's not a function to begin with because it fails the vertical line test. So this fails vertical line test, which implies not a function. So, which tells us, since it's not a function, it is not one-to-one. All right. So in order for a function to be a one-to-one function, it must first be a function. So it must first pass the vertical line test. After that, then we can check, well, does it pass the horizontal line test? And then we can say, yeah, okay, that would make it a one-to-one function. All right. Now, let's talk about this a little bit though, because algebraically we can consider something. So consider f of x being equal to x squared, and g of x being equal to radical x. All right. Algebraically, we have that f composed with g of x, in other words, f of g of x. Well, what does that mean? Plug in g of x into f, so we have g of x squared, so we have radical x squared, so we have x. And similarly, we can start with g of f of x. This means g composed with f of x, which again gives us g of f of x, which in this case means the square root of f of x, which would mean then the square root of x squared, which is just x. So in here, algebraically, we just found that it passes the rules of showing that they're inverses of each other. But let's look at this graphically. X squared is this, and the square root of x is that. But we just said that this cannot be a one-to-one function, so it doesn't have an inverse, right? Because it fails the horizontal line test. It is a function, but it's not a one-to-one function. So how is it that we can say, well, this algebraically, they are inverses of each other, but over here, graphically, they're not? Well, it turns out that what we actually need to do here is restrict the domain of f, So we must restrict the domain of f. And what do I mean by that? Well, we're going to restrict this so that we can actually pass the horizontal line test, all right? And what we're actually going to do here to restrict this is we're going to get rid of all these values over here on the left. So how are we going to do that? Well, let's just say this. If I've got f of x being x squared for x being greater than equal to 0, and then g of x being equal just the square root of x, well, this is what we get. We get f of x being, I'll do this in blue, x squared, right, for x being greater than or equal to 0. Let's draw that a little bit better. There we go. So that would be that. And then g of x, which I'll do in yellow, ends up being something like this. All right. Notice here that these are actually symmetrical about this line y equals x, which they should be, right? Because they would be inverses of each other. But we have to restrict the domain of f in order for these to actually be inverses of each other. Technically speaking, x squared and square root of x are not inverses of each other because x squared has this domain over here that allows for all these negative values. But the thing is, with inverse functions, the domain and the range must be the same. In here, the domain of this function includes negative values, but the range of this one doesn't include any negative values. So technically speaking, x squared and square root of x are not inverses of each other. However, when we restrict them, when we restrict f, it is. All right, so let's do an example or two on how to find what the restricted domain should be. All right. So let's say that I said restrict the domain so of the function f. So that the function is one-to-one. And therefore has an inverse function. So let's see. We're at example C, I believe. So example C. Let's say that we have f of x is equal to x minus 4 squared. All right. Now, how are we going to do this? Well, let's think about what this looks like. All right. X minus 4 quantity squared. Well, it's a quadratic, so we know it's a parabola. And then this minus 4 really means move to the right by 4, right? Because it's happening on the inside, so it's a horizontal shift. So what does this look like? It ends up looking like this, right? Where this value right here is 4. So what we're going to do here is we want to restrict this so that it actually has an inverse, all right? In general, we want to restrict the positive values. So what we're going to do is we're going to say, well, from here on out, that's the part that I'm going to care about, all right? That is the part that I care about. That's going to be the restricted domain. So what does that mean? We're going to have the domain be equal to 4 to infinity. Because 4 to infinity, in that piece right there, it does pass the horizontal line test, right? So therefore, it would have an inverse function. So all we're doing there is essentially taking the right piece of this parabola. All right. So now that definitely has an inverse function. Now, let's do another one. Let's say that f of x was something like 1/2 x squared minus 1, right? Now, what is the transformations happening here? Well, here, this just makes it it's a vertical shrink, right? On the outside, multiplying by 1/2, and then this minus 1 is shifting down by 1. So this is a vertical shrink. That's not really going to do much as far as the way that we graph it, but our shift down by 1 means that we got something like this, right? So now in here, well, what do we care about? We care about the piece that would stop repeating. In other words, a piece that would make it past the horizontal line test. So I'm just taking the right half of this parabola. All right. So in here, this would be my domain. So my domain would be from, well, 0 to infinity. All right. And this could apply for not just these kinds of functions. Let's also look at let's look at f of x being the absolute value of x plus 3. All right. Now, what does this look like? Well, it's an absolute value function, so it would look something like this, right? But we have this being shifted to the left by 3, so it would look something like this. Let's say that this value right here is -3, so it would be this. So what you can do again is just say, well, take this piece, right? And what is going to be the domain there? Well, the domain is going to be starting from -3, including -3, and going all the way up to infinity, all right? So that's what you can do there. So basically, once you have these, the graph of these, it becomes very simple because all you want to do is take the right half of whatever the graph is. All right. All right. So now, that is finding the domain. Now, but how do we find the inverse functions? All right. So hold on. That was finding the restricted domain. Sorry, needed to specify that. But how will we find the inverse function of, or the inverse of a function? All right. So let's see. Finding inverse functions. So find the inverse of the given function. And we're at f, I believe. No, D. Hold on. How did I go? C, D, E. This should have been E. There we go. E. F. All right, cool. I was right. We're at F. F. Let's say that we had something like f of x is equal to 5 minus 3x over x plus 2. All right, so how do we actually find the domain here? Well, the real answer to that is already stated in the definition. All right, if you recall, something I said was that the domain and the range they flip, right? I've been saying that they flip. So the x values become y values and the y values become x values. That right there is the actual idea. So what we're going to do first is we're going to rewrite this as y equals 5 minus 3x over x plus 2. All right. And what we're going to do here is we're going to flip the x and the y values. What do we mean? That means wherever I see y, I'm going to write x. And wherever I see x, I'm going to write y. So we have y plus 2 on the bottom. The next thing I'm going to do here is I'm going to solve for y. All right. And let's see. How do I solve for y here? Well, I'm going to multiply this to the top over here. So I end up with xy plus 2x is equal to 5 minus 3y. Then I'm going to put all the y's on the same side. So in other words, I've got xy plus 3y. And whatever doesn't have a y on the other side. So I end up with this 5 stay there. Move the 2x to the other side. So minus 2x. So essentially I did move this over here, move that over there. At that point, well, I'm solving for y. So I can factor out a y out of these two. So I have y times x plus 3 is equal to 5 minus 2x over, well, just 5 minus 2x. And then finally, we can say that y is 5 minus 2x over x plus 3. All right. And now we're done. Well, almost. The last thing we need to do here is write it as an inverse function. So we're going to say here that the inverse of f, right, because I started with f, it's going to be just 5 minus 2x over x plus 3. So, yeah, so again, essentially, you start by replacing the x and the y value and solve for y. Let's do another one. So that was f. G. Let's say that we had something like g of x is equal to the cube root of 10 plus x. All right. And we're going to start this the same exact way. We're going to start by saying, well, rewriting it as y equals the cube root of 10 plus x. Then we're going to replace the x and y's. So we have really x is equal to the cube root of 10 plus y. And then solve for y. So cube both sides. So I end up with x cubed is equal to 10 plus y. Solve for y. So I can rewrite this as y is equal to x cubed minus 10. All right. And at that point, well, our last step is to write it as in function notation. In this case, the name of this function is g. So we would say g inverse of x is x cubed minus 10. All right. Let's do another one. That was GH. So let's say that I have f of x being equal to the square root of 2x minus 3. And we're trying to find the inverse of that. Once again, we're going to start by saying, well, let y equal to the square root of 2x minus 3. And then rewrite this as x is equal to the square root of 2y minus 3. Because once again, we want to replace the x with y and y with x. So next thing we're going to do is square both sides. So I end up with x squared is equal to 2y minus 3. Add 3 to both sides. X squared plus 3 is equal to 2y. And solve for y by dividing by 2. So I end up with y is equal to x squared plus 3 over 2. All right. And in here, the very last step would be write it in function notation. So f inverse of x is equal to x squared plus 3 over 2. Let's do another one. Let's say that we had something like this. So we're h, so I. Let's say that we had f of x being equal to x plus 1 over x minus 2. And we want to find the inverse of that. All right. So once again, what do? The very first step is rewrite this as y equals x plus 1 over x minus 2. Next, replace all the x's with y and the y's with x. So we have x is equal to y plus 1 over y minus 2. Multiply this up here. So I have xy minus 2x is equal to y plus 1. move the y's to the same side and all the non-y's to the other. So I have xy minus y is equal to 1 plus 2x. I'm going to rewrite that as 2x plus 1. Right, so essentially I move this over here and this on that side. Next thing, in here, I see they both have a y, so I can factor out a y, and I have x minus 1 is equal to 2x plus 1. And finally, well, almost, solving for y, I end up with y is equal to 2x plus 1 over x minus 1. My final step here is to write this in function notation, so I can say here that f inverse of x is 2x plus 1 over x minus 1. All right. And that is the end of 1.9.
Wasn't that fun? If you think I made a mistake somewhere, you're probably right. Tell me all about it in the comments. If you feel you learned something from me in this video, hit the like button, hit the subscribe button, but more importantly, share it. Share this video with your classmates. And remember, you don't have to like math in order to be good at it. But you do have to be good at it. I am Jose Orozco. Goodbye.